So, dear colleagues, good afternoon, good morning, good evening. Let me start our today's seminar, which will be from Mohammad Amin, Quantum Annealing Beyond Optimization. And with one slide, I would like to introduce our today's speaker. Mohammad Amin is a chief scientist at D-Wave Quantum Incorporation and an adjunct professor at the physics department of Simon Fraser University. He obtained his bachelor degree in electrical engineering from Shiraz University, his master degree in physics from Sharif University of Technology, and his PhD degree in condensed matter physics from the University of British Columbia, Canada. Soon after, he joined D-Wave company, and since then he plays a key role in the development of D-Wave's large-scale quantum processors, as well as the theoretical and experimental understanding of their complex behavior. His expertise expands over many areas, including superconducting qubits, noise and decoherence in superconducting circuits, theory of open quantum systems, quantum critical phenomena, and quantum machine learning. His research has led to over 30 patents and more than 100 publications in high-profile journals, including the ones you can see. So with this, I would like to give the microphone to our today's speaker, Professor Amin, please, and stop sharing.
Okay, let me share. It is my great pleasure to give the presentation. I apologize for my dog barking. I don't know what happened. But it's my great pleasure to give this talk to your institute, especially because, let me just see. Oh, because Sasha Amelyanchuk was a great friend and my mentor. I said to Sergey that he was basically my postdoc supervisor, although I didn't do postdoc at D-Wave, but he played the role of a postdoc supervisor for me. This image is in a Persian restaurant when he visited D-Wave in early 2000s. So for those of you who don't know what we do at D-Wave, we make superconducting quantum computers. Our main product is a quantum annealers. Recently, we acquired a company called Quantum Circuits that we also do gate models. So now we do basically both. But on quantum annealer side, this is the latest generation of our superconducting quantum computer. It's Advantage 2. It has more than 4,400 qubits, 40,000 couplers, and each qubit coupled to 20 other qubits. It's 20-way connectivity. And we have on-chip superconducting digital circuit to program this. So it's I don't know, hundreds of thousands to millions of Josephson junctions working all together for this machine to work. We can perform forward annealing, reverse annealing, and coherent annealing. Coherent, I mean you can anneal faster than the coherence time. And we can do analog digital quantum computation. I will touch on these in next slides. This is the only equation I mentioned to Sergey. Let's see. What this machine implements is the transverse field Ising Hamiltonian. So it has two components, a transverse field part, which is basically sigma X Pauli matrices, and the longitudinal part, which is single qubit biases and couplers, and these both are programmable. There are two prefactors A of S and B of S that can be changed with one parameter. We call it S here. And as S goes from 0 to 1, A of S goes from a large value to 0, and B of S goes to 0 to large value. We represented this in energies so that we can compare it with temperature. The physical temperature is at black line. So you see in most area, important area, these energy scales are much bigger than temperature, but nevertheless, temperature plays an important role if we don't do fast annealing. I meant annealing. So by annealing, I mean that we gradually move the system from from a small s to large s. This is the direction of annealing. And at the beginning of annealing, your state is a superposition of all classical state, which is the ground state of the first term. And at the end of the annealing, if the annealing is slow, you end up with some low energy, a low energy classical state of this final Hamiltonian. And if you program it, you can actually solve optimization problems. But I chose the title of this presentation to be annealing beyond optimization because annealing sometimes to some people are synonymous to optimization. But I want to show that there are many other things you can do with this type of annealing quantum processors that are not optimization. And many of them are enabled by recent advances in QPU control. Okay, so I want to start from the first one, which is optimization, and then get to the other ones. Optimization, annealing for optimization was first introduced by this paper, seminal paper by Kirkpatrick et al. This is the paper that introduced simulated annealing, a numerical technique that still people use for optimization. It took 2 decades almost for people to think about a quantum version of that. This is a Kodawaki Nishimori paper, who was one of the first theory papers that suggested that. But the more important was this paper. It's an experimental paper by Apley et al. That tried to experimentally verify that quantum annealing can do something better than classical. But at that time, in 1999, that's when I graduated, there was no quantum annealers and there was no quantum computers at all. There was only people maybe have made one qubit with very short coherence time. So instead of running this on a quantum computer, they actually did it with magnetic materials. They picked some disordered magnet, the ferromagnet, and they annealed it 2 ways. They first annealed it by cooling it down, this is blue curve, to some place within the spin glass phase. And they also annealed it by reducing the magnetic field. So magnetic field orthogonal to the z direction of the ferromagnet. And so they both anneals ended up in the same point in phase space, in phase diagram, in glassy phase. And they concluded indirectly, because you cannot measure energy, you cannot measure the state, but you can indirectly by looking at AC susceptibility, they concluded that quantum annealing converges faster to the optimal state. Just to entertain you, this is the first check issued to D-Wave by significant amount of $4,000 to Jordi Rose. And the day of issue of this check is 1 month after the publication of this paper. And this paper actually was a big inspiration a few years later for us to move toward annealing. 1 year after starting D-Wave, here it is. We are two D-Wave employees, me and Tim Duty, in Utrecht, Netherlands, sitting with Gabe Apley, talking about probably how cool it would be if somebody could test their experiment experimentally, which sounded impossible back then, which, as I said, the state of the art was one very bad qubit. And this is the image of me and Gabriel Apley 24 years after. And so of course, we both aged. And so on the theory side, things was a lot harder. Of course, nobody could simulate quantum the annealing at such a large size, because if they could, you didn't need quantum computers. So people try to use quantum Monte Carlo as a proxy for quantum annealing, and this is the paper. It says theory of quantum annealing of an Ising spin glass by Santoro et al. But it's not really theory of quantum annealing. It's basically comparing two classical algorithms, quantum Monte Carlo versus simulated annealing. They plotted residual energy, which is the average energy minus the ground state energy, as a function of number of Monte Carlo sweeps, and they see that quantum Monte Carlo converges faster. The slope is faster than simulated annealing. But we should understand that quantum Monte Carlo does not simulate dynamics of quantum annealing. It's just thermodynamic equilibrium simulation of a quantum system, a stochastic quantum system. So the question remains, where would a real quantum annealing land on this graph? And it took another 2 decades for us to have large enough and coherent enough quantum annealer to test this. And this is the paper, a Nature paper we published now 3 years ago, 2023, testing this hypothesis using on 3D spin glasses. And you see that we did quantum Monte Carlo, we did simulated annealing, and we also did run this on D-Wave hardware. And you see simulated annealing quantum Monte Carlo looks the same. Simulated annealing is scaled a little bit worse than quantum Monte Carlo, but quite surprisingly, quantum annealing actually is scaled better. And so it scales better up to some point, and then you see the deviation from the straight line, and this is due to temperature. So if you could do quantum annealing coherently, you would follow this line, but then you see temperature actually shows up and excite the system out of ground state, and then you basically raise the residual energy. But even more interesting is that this could be predicted theoretically. The solid line is the prediction using a scaling argument, and we did it with in collaboration with Anders Sandvik, who is one of the experts in this field. And I'm surprised nobody did it before we tried to test it experimentally, because theoretically somebody could do it, even Anders could do it himself. But the most important thing is the experimental advantage that we observe over classical simulations, classical algorithms, can be supported by theory. And this is the first, and I would say the only, this is the first and the only theory-supported demonstration of quantum advantage in optimization. People talk about doing optimization using gate model, but there is no theory that supports that. But there is a theory that supports advantage in quantum annealing. Okay, if you look at, so as I said, the x-axis in this graph is Monte Carlo sweeps for quantum Monte Carlo and simulated annealing, but time in nanoseconds for D-Wave. If you do everything in time, in nanoseconds, you see that the gap, not only there's a scaling advantage, there's also a big gap in speed. This is versus one single uh, core CPU. And there's a big gap, it's in speed. And this is the gap to just reach the low energy, uh, a low energy solution with one of these techniques. But another question is, how about the statistics, not just the energy? And can these algorithms simulate the statistics? And the answer is no. And can it be simulated by any other means? And the answer is hopefully no. And if you can show that, that's called quantum supremacy. And this basically brings me to the second topic, which is quantum simulation. Actually, what we did up to in this 2023 Nature paper was quantum simulation. Our machine was simulating critical dynamics of a 3D spin glass, quantum going through quantum phase transition. But we didn't talk about how we perform compared to a classical algorithm. And this is what we did. We published last year in Science. And what we show is basically no classical algorithm can simulate what D-Wave does within the accuracy of the QPU. We called it quantum supremacy, but the editor asked us to change it to beyond classical because supremacy is a forbidden word apparently, but I don't agree with that. But nevertheless, this is the final, the most important and final graph of the paper. We simulated critical dynamics in four lattices. One of them, the first one was a square lattice, but we don't claim supremacy for that. So then supremacy was claimed for cubic lattice, diamond lattice, and bi-clique problems. And we run all three of them. We measure the error of QPU, and we demand classical algorithms to match that error. We don't demand classical algorithm to give you exact solution because that is much harder. And up to this dashed line, we actually could solve the problem classically and match it classically, and up to this size. And on the y-axis, it's what's the cost of GPU seconds. And you see that the cost grows exponentially. So up to this point, this dashed line, we did it basically numerically, and we confirmed the result agree with theory. Theory agrees with experiment. And beyond that, we extrapolated using area law of entanglement. And we have good evidence that area law is confirmed within the range that we could test it, and we could extrapolate using area law. And this is the extrapolation result. And just to give you some markers, this blue line is 1 million years if we use the fastest supercomputer at the time, Frontier, in Oak Ridge National Lab. Assuming that you could parallelize all GPUs and you had no memory limitations, which is basically impossible. And this line is the global annual electricity of the whole world. So what I'm showing is basically it's impossible. It is not possible to match what this QPU does at even not at the full scale. This is like 500 qubits. We have 4,000 qubits. At the level of 4,000 qubits, it's really, really unmatchable by any simulation algorithm that they can come up with. Okay, I want to jump to one more topic, which is related to simulations. And this is something we developed very recently. We call it analog digital quantum computation. So let me go back to the one equation I showed. So this is not another equation, Sergey, this is the same equation. So in annealing picture, I told you that we use this Hamiltonian and we uh, change these parameters A of S and B of S uniformly or monotonically in time. But recently we can do something different. We can use some qubits to apply gates on other qubits, something like that. So just very simple picture. Still within this annealing framework. This is an amazing technique that we have developed. And with that, we can actually do some unitary operations uh, to initialize the qubit in some state and do analog computation. So the analog computation that we do right now in the result that I'm showing is basically not changing S. We sit at one point along this diagram at one point like here or here, and then we just let the system evolve with constant Hamiltonian. At the end, we do another unitary evolution, which basically allows you to measure in any basis that you want. And this actually is completely new way we can manipulate this, and we can do a lot of amazing things. I'm going to show you a couple of examples. The first example is in 1D chain. So what we do is basically we couple 120 qubits. This is 60 and minus 60 is basically the position of the qubit. And we have 120 qubits, and we have periodic band boundary condition. So this one end is the same as the other end. We have periodic boundary condition. We excite one qubit at the center by a Hadamard gate. So imagine all the qubits are at zero in ground state, and we excite one qubit by Hadamard gate. You get superposition of 0 and 1. And what it means is you have basically one photon with probability 1/2. And then we watch how this one photon propagates along this chain by this weak coupling J. This is basically using rotating wave approximation. This is basically the XY model. It's hopping. And you see the photon hops and this is basically quantum walk. The photon propagates in both directions. Once it reaches the end, which because it's periodic boundary condition, you get interference patterns. So the wave interfere with each other, and then we get up to the end because and the total time is 20 nanoseconds. And even more interestingly, if you Fourier transform this plot using the fast Fourier transform, you get this plot. And this dashed line you see is what the theory predicts using Jordan-Wigner transformation, the fermionic dispersion relation. And you see the agreement between theory and experiment is stunning with no fitting parameter. We just put the Hamiltonian parameters and we just run this, and then it fits. It matches very well. So this gives us confidence that we can actually, this is basically a quantum simulation. We can actually simulate fermionic the dynamics now in 1D reliably and agree with theory. Now we can go to more complex problems that you cannot simulate easily, like you don't have Jordan-Wigner to give you exact solutions. Let's go to 2D. This is a 2D graph we have. It's a square octagonal lattice that we can embed very easily. Now what we do, we apply Hadamard gates on every other qubit. So every blue qubit is Hadamard gate, every red qubit is no Hadamard gate. This is a little bit past zero, it says 0 nanosecond, a little past it. There have been some dynamics, but it's hard to set the zero. And now we have a clean system with no disorder and disordered system. And the prediction is clean system, you should lose this memory quickly, and the system so-called thermalize in many-body localization language, which what it means is you lose the information and you get an ergodic state. And in disordered system, you expect to have many-body localization. So the information is not lost. The wave function will localize in some pattern. So let's run this and then show you what's happening. So you see within 2 nanoseconds, the left graph basically localized, and the right graph reaches some pattern, but you see some local oscillation. Let me run it again. So you see on the right graph, you get the pattern is stabilized, but you get some local oscillations. That's what you expect from many of the localizations, that you have local wave functions that oscillate. So this is an evidence of 2D local many-body localization, which is still questionable. Some people believe it's unstable at larger scale. Some people don't believe that. And now we have a machine that we can test it. This is 440 qubits. Because of some limitations of wiring, we can not go to larger than this, but in next generation, we may be able to go to 4,000 qubits and do this test at much larger scale. Okay, so maybe before I go to other topics, let me pause and see if there's any questions up to this point. I'm going to move away from physics the next slides.
May I ask
Yeah,
a
sure.
question? So regarding this particular figure, what is control parameter that make these systems different, disorder and clean in experiment?
Very good question. So we have this transverse field Ising model, but the transverse field is much bigger than the coupling. Therefore, coupling plays the role of hopping, and transverse field plays the role of the energy. If the transverse field is completely uniform, we actually shim them to be completely uniform. You get clean system on the left. On the right, you basically make transverse field. We add some random disorder to the transverse field. And we can do this at different levels of disorder and see what's the effect of disorder. Basically, you're on the left, the photons, better to think about it in terms of photons. The photons can just propagate with no barriers, with no disorder. On the right, the photons are seeing some disorder energy potential.
I see. So, and related question to this, is it possible to make the coupling, the disorder in coupling strands, or this is
We
not
can do,
possible?
absolutely, we can do that as well. If
Okay.
you have any suggestions, but this is something that experiment that people have proposed. There was actually a Chinese paper which did exactly the same thing with 70 qubit, and they claimed there is no many-body localization, and we proved them wrong. At least we see that this is stable, and there's some quantity called imbalance, which is the difference between the initialized sites that you put photon and not sites that you don't put photons. And this imbalance should go to 0 if you get ergodic state, but this imbalance should stay finite if you have any localization. And we see completely this stays finite. So yeah, this at least we show that paper is wrong. But I'm pretty sure there are many other things we can do. If you have some suggestions, we can test.
Thank you.
Okay. Any other questions?
Speaking about qubits, will you tell later maybe what are these, how they're realized, coupled, how, which are
Okay, I
the
can tell right now. So these are flux qubits. These are superconducting loops that are coupled magnetically. The couplers are also another superconducting loop, which you can tune the shape of the current phase relationship by just some loop of Josephson junctions. And yeah, so then we can actually tune coupling by another flux between them. But these are just superconducting loop called RF squid flux qubits. That's what we do. If you have any other detailed question, I can give you one.
how are they coupled, those 400 qubits?
They covered magnetically by other superconducting loops.
By clusters or by next neighbors only?
Oh, this is a very complicated graph. As I said, every qubit is coupled to 20 other qubits.
To 20, I see.
And this allows you to program many different graphs. Like we programmed 3D graph, we programmed diamond graph, we programmed bicyclics. We can also program much more complicated graphs. So every qubit is coupled to 20 other qubits. The graph is called Zephyr. If you go to D-Wave website, you can see what it's even hard to explain how it is. It's a very complicated connectivity.
Thank you. One more question from Oleg Turtanov.
Yeah.
How many qubits can you put in entanglement at once?
It is a very hard question because you don't even know how to measure that. But from, let's go back. In this paper, we simulate what this machine does classically. And we see that the correlation that is there is no environment, so we cannot say this correlation is classical. There's no environment. So there are some correlations built up through Kibble-Zurich mechanism. And we have evidence that this correlation covers the whole system. So at least in this experiment, we are kind of confident that the entanglement covers, so we go up to like 500 qubits here. So the entanglement basically spans over the whole 500 qubits. But there's no way to measure that. But because otherwise the classical algorithm that we used, which was tensor network MPS, matrix product state, which was the only one that could go to these sizes, would be able to simulate. So the metric, this technique, matrix product state, is directly sensitive to entanglement entropy. And what we actually calculate as a measure of complexity is how the entanglement entropy scales, which is basically bond dimension of matrix product state. So at least at this point, with this experiment, I can say it is the 400 or 500, I don't know how many, 400, 500 qubits that we have, this largest one that we have here, entanglement is system spanning.
It's amazing number.
Yeah.
Thank you.
Any other questions? Okay, so
Gleb Skorobogatka wants to ask.
Okay. Do you hear me?
okay, go ahead.
Do you hear me?
Yes,
Yes.
yes, please.
Okay. It's related to previous question. Does it mean that it is hard to isolate any part of your system from the rest for the purposes of algorithm, for example?
Yes, so we actually tested all of these. We tested whether it is possible to simulate some part and then patch together. We tested techniques such as PEPs, which naturally do that. I should say that to be more clear, some people, this diamond graph is the loops in diamond graph are bigger than loops in cubic lattice, and biclic has a lot of loops. So biclic is no question. There were papers after that they claimed the basically loops are big and they could simulate diamond graph at a small fast times up to like 7 nanoseconds or something. So we claim 7 nanoseconds diamond supremacy. They claim that they can do it, but they didn't. They did it at very small scale and they said, oh, we can do 7 nanosecond larger scale. They didn't say, okay, really how much really it takes based on the scaling of there. So it for supremacy, we use a scaling just to argue, but supremacy they should do, or at least say this is how much it takes. If it takes, I don't know, a year instead of a million year, still it's very hard. If it takes 10 years, I would say it's edge of supremacy. But I should say for the diamond, some people claim that it's easier than the others. Biclic, nobody actually even dare to tackle because it is highly connected, highly entangled. It's very hard to do by any other means.
Does it mean that for quantum supremacy hypothesis, it's important to know that any entanglement spreads over the system with uniformly on all time scale? So I mean that in the beginning of the dynamic simulation, all processes of entanglement proceeds faster or slower than on the late stages. So how this is it important at all?
Yeah, absolutely. I think the reason these things become harder as a function of time. Actually, I shouldn't don't. Yeah, so this is 7 nanoseconds. We show only 7 nanoseconds, 20 nanoseconds here, but we do it as a function of time. And if you do it fast, it becomes easier because the entanglement does not spread enough. I think for below 7 nanoseconds for some of these graphs, PEPs can do it. So absolutely. So entanglement is actually the most important key. Absolutely. So we try to do this area law of entanglement, but area law of entanglement is relevant for MPS to some extent. For PEPs, if you get localized, if you get local entanglement, PEPs can handle it. So that's why, like below 7 nanoseconds, PEPs could handle some of these.
Well, I think with that
Thank you.
maybe we'd better continue and leave the
Sure.
question to afterwards, because
Okay, sure. So let me continue. I'm going to move toward applications, and it is less physics, so maybe for you guys it could be less interesting. So the other applications than quantum simulation. So the both applications that I mentioned was quantum simulation, but other applications is also possible. One of them is quantum artificial intelligence. So nowadays you guys are used to the chat GPT, and everybody has used it probably, and it's as amazing as it is that you answer questions and it gives you very uh, reasonable, plausible answer. It's just a way of guessing probabilities. Yeah, it is not magic. It's just a neural network predicts probabilities of a word subject to previous word and subject to the prompt that you use, and that's all. And we know that quantum mechanics is all about probabilities. So is it possible to use quantum probabilities for generative AI? And this is quantum generative AI. So quantum computer tries to learn probabilities. We did a preliminary work in 2018, published in collaboration with others, called quantum Boltzmann machine. And the goal was yes, if you have a Hamiltonian. So I have this equation, but Sergey, this is exactly the same equation that I used before, but written in different way that people use for machine learning. So if you have this kind of Hamiltonian, the last two terms is what people usually use for Boltzmann machine. But now you have this additional term, this transverse field that we do. And the question we ask is whether you can do machine learning with this Hamiltonian, which means can you learn some distributions? Can you train or match these coefficients B and W, which is our H and J, to learn a distribution? And the answer we found is yes, it's possible to do that. And that quantum Boltzmann machine paper initiated a field. Now hundreds of papers have been published studying different aspects of quantum Boltzmann machine. But what we care about is real world applications. So we found that in order to use a QPU, a hardware like D-Wave, it's not ideal to try to learn the data distribution itself. You better use a autoencoder. What autoencoder is, you have some training data, like these images of dogs. By the way, this is my own dog, the Milo, who you heard earlier. And you basically encode this space into some latent space, which is like binary numbers. So you have an encoder and decoder that translate this image into some binary numbers and then translate back from binary numbers to the same image. And your goal is basically the images look the same or approximately the same, if not exactly the same. And at the same time, you have another model, that learns what distribution appears in this latent space, and we call this prior. If you train this well, then you can basically sample from the prior and pass it through the decoder and you generate another image. And hopefully you can generate images of dogs that don't exist in outside. So this is generative, the core of generative model. And our goal is to replace this prior with our quantum computer, or we call it quantum Boltzmann machine. And we did that. We published papers a long time ago, but now there are actually applications, many applications of this very technique. So one of them was in high energy physics. My colleagues, my friends at Triumph which is a high energy physics accelerator in Canada, published this paper trying to learn the data that comes out of high energy physics experimental experiments using these quantum variation autoencoders. And they also published another paper. I don't want to go to details. You can look at these papers and learn the details. We recently collaborated with a company in Japan called Japan Tobacco on drug discovery application. By the way, the model we use is transformer model, very similar to language models, the same as language models like GPT. But instead of the model tries to predict words, the model predicts the symbols that if you put it together becomes a molecule. And we succeeded. We submitted the paper to the archive. It could appear anytime, maybe even today, I didn't check. And this is a recent work we have done in D-Wave. We tried to generate images with the whole QPU as a prior, 4096. And these are the images that we could generate. Again, these are not real people. These are basically images that our machine hallucinates. Okay, and I want to go to the last topic so that we can get to this, because I have to drop at 9, maybe at 5 minutes. I have another meeting. But the last topic is blockchain. Many of you may not know, or some of you may not know what blockchain is. So I actually have some cartoon introduction of how blockchains work. So imagine two people who don't know each other and who don't trust each other who want to do a transaction. And how can they do transaction in a secure way while they don't trust each other? A traditional way, which goes back to thousands of years ago, is just to pick an authority. The authority basically documents your transaction, and the authority has a power to punish the violator if any violation happens. And as I said, this goes back to thousands of years ago. You may know that actually writing was invented by Sumerians just to record transactions. And these are two tablets from two clay tablets from Sumerian time. The left one is one single transaction, and the right one is a block of transactions. So this is the word where the word block in blockchain comes in. There's a block of many transactions in one clay tablet in Sumerian time. And if they could chain these blocks together, they would have invented the blockchain, but they didn't. So what does this mean? So how can you do this secure transactions if there's no authority? So another way, if you don't have single authority, you can actually look at you can find a group of people, a lot of people, to witness your transaction. And then you go to majority vote if somebody wants to violate, to see if there's a violator or not violator. And that makes it hard. So if you want to cheat, you have to basically convince or bribe more than half of the witnesses. And if the number of witnesses is large, it costs a lot to basically bribe so many people. So it's not economically efficient to actually cheat. So you want to do the same thing with computers. So you want to have a network of computers probing and recording transactions in we call distributed ledger. Every computer has a record, and then you cannot change it. You cannot, and nobody can cheat because there's no way to change it. And if you want to change it, you have to, because it's majority vote, you have to basically convince more than half of the network that your change is valid. And it's very costly to do it, to have control over more than half of the networks that do that record the transactions. So the way it works is you have block of transactions, you chain them together, but now what chain means is cryptographic hash. So what is a hash? A hash is basically when you're converting an arbitrary length input into a fixed length output. A most common example of hash that everybody is familiar with is postal code. So any address, I mentioned Vancouver, Canada, for example, any address can be translated into 6 symbols, postal code, no matter how long the address is. And in terms of, for the case of postal code, it's reversible, it's two-way. Once you know the postal code, you know where the address is. But if you do it one way, so that you can just go from the address to a postal code, but there is no way to get from the postal code where the address is, this is called cryptographic hashing. And this allows you to just do one-way chain of every block subject to all previous blocks. And if somebody wants to go backward, it has to reverse this action, and it is not possible. So because of that, no information can be changed or removed from a block, and the block is distributed within the whole network, and it's very, very hard to cheat. But how can you make thousands of qubits computers participate in your blockchain? This is something called mining. So basically, make a competition, a puzzle that everybody should solve, and you just give reward to one winner. And by solving the puzzle, you require everybody to basically validate transactions. So a lot of people will validate transactions for just to win, and just one person win. And that basically motivates a lot of people to just win this big amount, big Bitcoin reward to participate. I just want to go to the details. The difficulty with this current way of doing Bitcoin is it's significant waste of energy. If we could replace the puzzle with the quantum puzzle, which is basically our quantum supremacy puzzle, then everybody had to use quantum computer to solve, and the energy cost would go significantly down. And this is what we did in this paper, blockchain proof of quantum work. We run a blockchain on 4 quantum computers, distributed in Canada and the US, and we show that it can be run stably. I'm going to just show you. This is how the blockchain working in progress. So every point added is a block added to the blockchain, and you see the chain. I don't want to explain what these different colors are. Some of the chains are disregarded, some of the chains are accepted, and that's how the blockchain works. So with that, I wanted to go to conclusion and have some few minutes for questions. I just showed you with advanced controls, our quantum annealing processors can be used for many applications, not just optimization, while optimization is still a useful application. I showed you that the generative AI and blockchain, it could be 2 examples of such applications, and I also showed you that analog digital quantum computation opens a new avenue for quantum simulation and many other things. With that, I want to thank your attention and open for questions. Thank you.
Yes, thank you so much, Mohammad, for telling us in such short term about so many diverse applications.
You're welcome.
We have, I understand you are limited in time, so we have not so much question. Please, dear colleagues, ask short questions. Yes, Oleg, please.
First of all, thank you very much for your explaining of the blockchain technology and procedure. It was very interesting. May I go back to this question of the number of qubits? As I
Yes.
understand, the single qubit can have decoherence time about 1 millisecond. But if you make your operation in a few nanoseconds with your annealing, you can maintain this entanglement of a huge number of qubits because of the operation is very short in time. Is
And
it correct?
the coherence time of the system is around 20 nanoseconds. Qubits.
Yes. For a single qubit, it's up to 1 millisecond, but for an array, for a large array, it's dramatically lower. So if you have a decoherence time larger than the operation time, it's okay.
Yeah.
So you can have put an entanglement a few hundred of qubits for a few nanoseconds and to make you all the operations.
Yeah, so we have the evidence. Yeah, you're right. So we have evidence that up to 20 to 50 nanoseconds, we follow coherent dynamics. We everything that we measure agrees with coherent dynamics, but after that, we see that temperature is actually changing our results.
So
Yes.
they are coherent during those 20 nanoseconds.
That's right. Yeah.
Thank you very much.
You're right. And we see that this 20 to 30 nanoseconds is enough to propagate entanglement to the whole system, especially when in biclic, so everything coupled to everything else. It takes almost like few nanoseconds for everything to be entangled to each other. That's why this biclic is very hard, because the distance is just 1, 2. I mean, it's very, very hard. So everything is coupled to everything else by two hops.
Sure. Thank you.
You're welcome.
Other questions? Well, since it seems not to be the case. Yes, Andrei, please.
Yeah, maybe a short question about energy consumption. Assume we take your argument that there is much lower energy consumption. Then everybody then buys quantum computer, and then the market grows extensively. Would it really result in the reducing the consumption, or just its temporary effect then?
As long as the cost of buying and running quantum computer is not dominated by energy cost, which is significantly the case here now. So to make a quantum computer, and it's not energy, it's the cost is much bigger. Then if, I don't know, in 50 years, quantum computer becomes so cheap, and then the dominant, because the energy cost is so low of quantum computers. So you have to reach a point that, okay, now the energy cost is because you need some penalty. You need some penalty for the people not to buy a lot of GPUs and just because even if you buy a lot of GPUs, you have to pay energy bill. So the penalty now is now cost of quantum computers. The cost of buying a lot of quantum computers and try to be more than half of the network is so huge now that nobody does it. So you basically try to be one node within then cheat by overcoming the half of the network.
Okay, so you mean that there is another bottleneck, like technological bottleneck or
Yes,
cost?
yeah.
Mm-hmm.
Yes, yeah.
Okay.
Yeah. More than energy cost. Yeah, technology cost is more than energy cost. No. And if anything, the money that is spent is used in good direction. The technology develops, not just wasting energy and so. If the money goes to technological development, that's a good way of wasting money than on energy.
Completely agree. Thank you.
Okay, thank you very much. Thank you for your attention. Thanks for your invitation, and hope to see you
Yes,
guys
thank you,
soon.
Dr. Amin. Thank you so much for the lecture, for being with us today.
You're welcome. Thank you. Bye, everyone.
Dear colleagues, goodbye. See you next time. All the best.
Bye. Thank you very much.